Okay, hopefully you've had a chance now to read in the textbook examples 9, 10, and 11. We're going to do some examples like those involving our class. So these problems involve three principles. The counting principle, so this will be the first thing it involves, and that is if there are two independent events, let's call them A and B, and there are m ways to do A, and there are n ways to do B, or maybe I should say arrange B. Then there are m times n ways for A and B to occur. Okay, so that was what we had learned in the first set of lessons. And then there were permutations. This is where order matters. Okay, and that was that the permutation formula was n factorial over n minus r factorial. And then there were combinations where order does not matter. And that was C of n comma r, n factorial over r factorial, n minus r factorial. Okay, so we're going to put these three things together in a couple of simple problems. Okay, so example one. There is a contest in math poetry. A team must have 2 boys and 2 girls. How many ways can our class be arranged to make these teams, or to make a team, I should say? Okay, so important information. We have 7 boys and 4 girls in the class. Okay, but what we need to do here is actually look at this as 2 different events. Okay, so event A is that we're going to take 2 out of 7 boys. Now the order doesn't matter. It wouldn't matter if we pick Kevin and then Andrew, or Andrew then Kevin. If we drew people out of the hat, they would both be on the team either way. So this is a combination. We have 7 boys, and we're taking 2 of them. So it would be, 7 factorial over 2 factorial, 5 factorial. That's an easy one to do by hand. That would be 7 times 6 times 5 factorial over 2 times 1 times 5 factorial. The 5 factorials cancel, and so you're left with, it looks like, 21 ways that we could choose 2 boys. Event B is how could we choose 2 girls? All right, so this would be the combination of 4 comma 2. That's even easier to do by hand. That's 4 factorial over 2 factorial, 2 factorial. So that's 4 times 3 times 2 factorial over 2 times 1 times 2 factorial. Cross those out, and it looks like there are 6 ways that we could choose 2 girls from the 4 girls in the class, right? So now we have 2 totally independent events. Clearly, the number of boys in the class and the way they were chosen had no bearing on how the girls were chosen. So in order to figure out the total number, we'll simply use the counting principle now and say that since there are 21 ways to choose the boys and 6 ways to choose the girls, I believe that's 126 possible combinations. Okay, so you can see how we use the idea of the counting principle and the idea of combinations in that problem. Okay, the next example. This will be example 2. Owen is going to make a seating chart. Where all 11 students sit around the U class. The desks are in a U in consecutive, that means next to each other, seats. How many ways can he do this? Okay, so when you look at this, the order definitely matters, all right? So we have 11 students in the class. The order definitely matters, so it's a permutation. So to answer this, I'm going to call this part A, because we're going to put some restrictions on this. Part A, how many ways can he do this? This would be the permutation of 11 things taken 11 at a time, which is just 11 factorial over 0 factorial, or 11 factorial. In fact, you probably could have said, well, there were 11 places we could put the first person, or for the first seat, there are 11 people to pick. There are 10 left for the second seat, and so on. So the answer is 11 factorial ways. I'm not going to compute that. That's going to be a very, very large number of ways that he could do that. Okay, but usually when you make a seating chart, there are restrictions. Okay, so let's put a restriction in here. What if the Darrows must sit next to each other? They can't bear to be apart even for a minute. So they must sit next to each other. So if that were in consideration, that would change things a little bit. Okay, so what would we have to do if they had to sit next to each other? Hopefully after reading example 11, you might have some ideas. Okay, the first thing that happens here is they're really now, we're down to 10, I guess 10 blocks, because the Darrows count as one block and every other student counts as a block. So there are 9 non-Darrow children in the class and 1 pair of Darrows, okay? But the Darrows can switch, we'll just say left and right. So we don't know if Joshua comes first or Genoa comes first, okay? They could switch back and forth. So that ends up giving us, this is almost like an event B. So we kind of have an event A here and event B here, all right? So we have to figure out the number of ways that the 10 blocks can be put together, and that would be P 10, comma 10, because we're going to use all 10 blocks. And so like in the last example, that will be 10 factorial. But since the Darrows can switch left and right, we will then multiply that by 2. Okay, so the answer is 2 times 10 factorial. So now that will not be as big as 11 factorial because we're multiplying 10 factorial, 11 factorial. I think up here that would be 11 times 10 factorial, which is definitely bigger than 2 times 10 factorial. So by making the Darrows sit next to each other, it would actually lower the number of ways Mr. Owen could do his seating chart. In fact, every restriction lowers the number of ways the seating chart will work. So if you have more and more students, you either need to put next to each other or keep apart, it becomes harder and harder to find ways to do it. In fact, let's do part C. If the Darrows may not sit next to each other. Okay, so we need to redo it with the Darrows not being allowed to sit next to each other. Okay, so how do we tackle this? Well, this is really like part A and part B put together. Okay, so if you look at part A, it has all of the ways that students could be seated, but part B is all of the ways that the Darrows would be next to each other. Okay, so what we're going to do is we're going to take all the ways that students are seated minus the ways that the Darrows are next to each other. Okay, so if you look at that, that's just the answer to A, which was 11 factorial, minus the ways that they are next to each other, which was 2 times 10 factorial. So if we look at that, oh, in fact, we could simplify that because we just said 11 factorial is 11 times 10 factorial minus 2 times 10 factorial. So if we wanted to, that is 9, I'm sorry, let me erase that. If we factor out the 10 factorial, that's 10 factorial, and what's left is 11 minus 2. So it ends up being 9 times 10 factorial. All right, so there are a lot more ways that they could be seated away from each other than next to each other because they're they make up a small percentage of the class. So that's how we could do that problem. All right. Now let's see. Let's just throw in one more problem with our class. Okay. Our class. So this is example 3. Our class needs. I don't know why we need this. We need a president, a vice president, and a pair of treasurers. It's always good to have 2 people looking after the money, 2 independent people so that one can't embezzle the funds that we create. Treasurers. Sorry, that's ERS on the end. Okay. And so we want to figure out how many ways we could do that. Okay. Well, let's assume that we first get a president and vice president. It doesn't matter whether we do that first or second. You can go back afterwards and see that it would work out mathematically to be the same answer if we picked our treasurers first and then our president and vice president. Now, we're not going to run an election. People get their feelings hurt. We're just going to draw names out of a hat, and we want to figure out the number of ways we could pick all of these. Now, what's interesting about this, the president and vice president, it does matter for picking names out of the hat. If the first name is the president and the second name is the vice president, it does matter what the order is. Okay, so this is a permutation. The order matters. So we have 11 people in our class, and we're picking 2 of them. So that's 11 factorial over, let's see, that would be 9 factorial for the permutation formula. Now for the treasurers, it doesn't matter the order. It doesn't matter if it's Joshua then Genoa or Genoa then Joshua or any other 2 other people in the class. So that's a combination. Oh, but what's interesting here is there are no longer 11 students to choose from. 2 of them are already in the high offices of president and vice president. So now there are only 9 students left from which to pick the 2 treasurers. So that becomes 9 factorial over, we're picking 2, so 2 factorial, 7 factorial. And so then the total answer is the product of A and B. So it's 11 factorial over 9 factorial times 9 factorial over 2 factorial, 7 factorial. And you could see some things simplify. The 9 factorials cancel out. So we could say this is 11 times 10 times 9 times 8 times 7 factorial, stop there, over 2 factorial, so call that 2 times 1, 7 factorial. Back to red, the 7 factorials cancel. The 2, oh, that goes nicely into the 8, so that's a 4. So you could just multiply all of this out and get your answer for how many ways we could fill these offices for our class. All right, so those are like the more complicated problems in the text. Have fun with the homework.